Okay, folks. So yesterday we learned about the Wolfram test for heteroscedasticity. Yeah, you remember the Wolfram test for heteroscedasticity? What is that test? How do you take the Wolfram test? So you have the data, you break it into three parts, and then what do you do? You do a regression in the first part, you do a regression in the second part, and then second part you don't do, the last part you do, and then you compare the variances using the F test. But you arrange the data in increasing order of X. Right? Now that's the Achilles heel of the model. Because if you have not X, but X1 and X2, two explanatory variables, so you're not sure which X2 increase in a, arrange in increasing order. Right? Okay, which X2 put things in an increasing order, and therefore the test is not a very, it's historically important, but you don't really do it nowadays. You don't find many research papers using the Wolfram test. Okay, so we have more generalized tests. So one general test is, so suppose you have the following model. Yeah? Alright? And you suspect that the x, z variables, x or z, y is correlated with, so the error term is, the variance of the error term is associated with, has something to do with x and z. Right? Sure? Okay? So how do you go about that? How do you go about testing this? So what you do is, the first step, carry out the regression. Right? And obtain E hat I. Sure? In the second stage, E hat I square. So E hat 1 square, E hat 2 square, E hat 3 square, E hat 4 square, and so on. Right? Now note that E hat 1 square is an estimator for the variance of sigma square. Sigma 1 square. E hat 2 square is an estimator for the variance of hat 2 square, and so on and so forth. Right? Then do the following regression. So regress E hat I on gamma plus delta 1 xi plus delta 2 zi plus some error term to bi. And now you have to use this to test the null hypothesis of no heteroscedasticity. So how will you test the null hypothesis of no heteroscedasticity? How will you test the null hypothesis of no heteroscedasticity? In this case, what will no heteroscedasticity boil down to? What does heteroscedasticity mean in this context? Variance of error term changes, and changes with what? X or Z. So if there has to be no heteroscedasticity, the variance of error term should not change with X and Z, but be constant. So in the context of the equation 3 that you got, what does that mean? When will the variance of error term not change with X and Z? In the context of that model, what do you think? You need to impose some restrictions, for that to be true. What are those restrictions? So if you have to say variance of error term does not change with X, what restriction does that entail? What will be the value of del 1 in that case? if the variance of the error term has nothing to is not to be associated with x, what will have to be the value of del 1? What will have to be the value of del 1? 0. Yeah? Value of del 1 will have to be 0. Similarly, what will the value of del 2 have to be? 0. If z and the x sigma square have nothing to do. So the fact that the null hypothesis that there is no heteroscedasticity boils down to testing the h naught right? Del 1 is equal to del 2 is equal to 0. Right? Okay? Against the alternative that del 1 or del 2 or both not equal to 0. Can somebody explain this to me? Why does the null hypothesis del 1 is equal to del 2 is equal to 0 means there is no heteroscedasticity? So if both del 1 del 2 are equal to 0, what is that equation left with? Gamma and Vi. So E at I square is what? Gamma plus Vi. So what is the expected value of E hat I square then? The expected value of E hat I, if this is 0, if this is 0, you are left only with gamma and Vi, and Vi has been 0. What is the expected value of expectation E hat I square? Gamma. But what is meant by the expected value of E hat I square? What is it an estimator of? Sigma square. Expectation E hat I square is the average value of E hat I square, which is nothing but the variance, sigma square. So if del 1 and del 2 is equal to 0, what does expectation E hat I square become? Gamma, which is a constant. So which means that the variance of the error term is constant in the original model. So there is no heteroscedasticity. Right? On the other hand, if either del 1 or del 2 are not equal to 0, what does that mean? What does that mean if del 1 and del 2, either of the del 1 and del 2 are not equal to 0, what does that mean? There is? No, but the variance of the error term changes with x and z. So there is heteroscedasticity. So therefore testing the null hypothesis of no heteroscedasticity means testing for del 1 is equal to del 2 is equal to 0. Again the alternative that at least one of the dels is not equal to 0. Is everybody getting this? Yes. Sure? Okay? Now there are two ways in which you can test. If you generally know that the error term is normally distributed, then this is actually an F test. Have you did this in a multi-distribution model testing for coefficient restriction? You did. I'll do that with you after a few minutes, right? So del 1 and del 2 is equal to 0. Normally it would have been an F test if the error term is normally distributed. But if the error term is not normally distributed, we are not sure. So then it's not necessarily an F test. So what does one do? In which case, one takes a test called a Lagrange multiplier test. It's called an LM test. Okay? Lagrange multiplier test. LM test. Okay? LM test. And what does one do? One conducts this regression. One carries out this regression. Calculates the R square of this regression. You come across the term R square? No? So let me finish this and come back to your question. Right? R square of the regression. Sure? Okay? You multiply it by the degrees of freedom that you have here. Call it n. Okay? So what you do this regression, calculate the R square of this regression, multiplied by the degrees of freedom. Alright? Okay? And under the null hypothesis, this follows the chi-square distribution with the number of degrees of freedom equal to the number of restrictions that you have imposed here. In this case, how many restrictions have you imposed? 2. right? So this follows the chi-square distribution with 2 degrees of freedom. This follows the chi-square distribution with 2 degrees of freedom, right? Under the null. So what do? You actually calculate n r square. The residual sum of squares by the total sum of squares. 1 minus the residual sum of squares upon the total sum of squares. You know what the residual sum of squares is? Summation e hat I squares. Right? Okay? The R square is the formula. I explained to you what an R square is, what it does and all that. Right? Okay, so chi square, it's chi square with 2 degrees of freedom. And R square is chi square with 2 degrees of freedom. Sure? Now, heteroscedasticity can come about because the model is misspecified. Heteroscedasticity can come about because the model is misspecified. Right? And what do you mean by misspecification? It means that the error term that you have is not merely a pure statistical difference between each individual value and the mean for that value. There is some other explanatory variable involved. Right? In which case, this test needs to be generalized. This is called the Breusch-Pagan test. Okay, this is called, what we have done here is called the Breusch-Pagan or the B2 test for heteroscedasticity. Okay, Breusch-Pagan test. We have after the name that two statisticians who wrote the paper. Breusch-Pagan test for heteroscedasticity. Okay? Sure. Breusch-Pagan test for heteroscedasticity. Now, because heteroscedasticity can come about also because of a specification error, this test can be generalized also to test for specification errors. Right? So, for example, if you increase this, if you expand this and say xi zi plus vi, right? Xi zi plus vi, and then sure, and sure, again it's the alternative. Then this test also tests for whether the variance of the error term, then there is misspecification in the error term. Right? Misspecification in the regression equation, whether heteroscedasticity is coming from misspecification as well. Right? And it's called White's test for heteroscedasticity. White, after the an econometrician named White, it's called White's test for heteroscedasticity. The delta 3.
Delta 2 xi z.
Delta 3. Delta 1 xi plus delta 2.
Gamma plus delta 1 xi plus delta 2 xi z.
No, delta 2 zi plus delta 3 xi z. एक additional term है. So delta 1 xi plus delta 2 zi plus delta 3 xi z. Where you multiply, there is a product term xi z. Right? And if you want, you can even take powers of the test, powers of xi square, zi square, and so on and so forth. You can make it a more general kind of a, right? Okay, which now will be chi-square 3. Why? 3 restriction, perfect, right? Chi-square with 3 degrees of freedom. Sure? Okay? Alright? Okay? Now, so these are the generalized tests for heteroscedasticity. Now you will be wondering what is this R square. So let me take you also to the R square idea. Right? R square, adjusted R square and so on. And also the F test in general, which can be used if the error terms are normally distributed. Right? So, so think of a regression where alpha plus beta xi plus ei. We have right? And suppose you have y hat I. Yeah? Which is what? Okay. And say suppose you have e hat I, which is y hat I minus y. Right? Y hat I minus y. Sure? This can be written as sure. So I can add and subtract y bar. Right? I can add and subtract y bar. Okay? All that I have done is I have added y bar and subtracted y bar. Minus y bar plus y bar. Yeah, minus y. I'm sorry. Minus yi. Okay? Okay? Y hat I minus y bar plus y bar minus y. Right? Sure? I can easily write this. Okay. Now, there are three things that we are interested in. We put a total sum of squares, which is summation yi minus y bar square, which is the total variation in y. Okay? Then I have got y hat I minus y bar square. What is y hat I minus y bar square?
E hat square.
What is y hat I minus y bar square? So y bar is the mean of y. Y hat I is the explained, the condition. So basically y bar is the mean of y. Y hat I is the condition mean of y for a fixed value of x. Right? Okay? So which is the deviation for that particular value of x, the mean of that particular value of mean of y for that particular value of x, its gap from the overall mean for y. Y hat I is the conditional mean for y. Y bar is unconditional mean for y. Right? Now why is y hat I different from y bar?
Because y hat doesn't consider x, it's condition.
Yeah, y bar doesn't consider x. Y hat I considers x, right?
Exactly.
Y hat I considers x because the specific value of x. That is alpha hat plus beta hat x. So that is y hat I. So which is the explained part of the regression. So this part is what is explained by the regression model. This part is what is explained by the regression model. So we call it the explained sum of squares. Right? We have one total sum of squares, explained sum of squares, right? And finally you have e hat I square. What is e hat I? What is e hat? What is ei? Error meaning what? Residual meaning what? That's why there's different names, no? What does it stand for?
Each variable of y minus mean of y.
It stands for each value of y. It stands for the difference between each value of y and the conditional mean of y given x. So it is that part of y which is not explained by our model. Whereas y hat minus y bar is that part of y which is explained by our model. Right? So this I will call the residual sum of squares. RSS.
Sir, so EI should be yi minus y hat. Initially.
What?
EI hat, each individual.
But I put a square, no? EI can be both actually, depends on how you look at it. Right? Yeah, so if you prefer to write it like this, we write it like this. Right? So in this case, this will change a little bit. My derivation would not have changed. Right? Minus. This is what you want it to be, right? But actually in the ultimate analysis there are squares involved, so it doesn't really change. It doesn't really matter. Right? Okay? Y bar minus y hat I and so on. Sure? Right? So there are three parts involved here. The total sum of squares is the explained sum of squares. There are two parts of it, right? The total variation in y, a part of it can be the explained variation in y, and a part of it will be the unexplained variation in y. So deviation of y hat from y bar tells you why the average the expenditure. So basically, if you have a household, so suppose the mean expenditure of all the households in Mumbai is 5,000, right? The mean expenditure of households which have income equal to 7,000 is 6,000 rupees, right? Y hat I minus y bar is just 1,000 rupees. And why is this 1,000 rupees? Why is this 6,000 not 5,000? Because incomes are different. So that's the explained part of the regression, right? And finally, think of each individual household, which will have say expenditure equal to just 2,000 this month. So the gap between 6,000 and 2,000, which is minus 4,000, is the individual specific gap which is not explained by the model. If you square all those gaps, then you got the residual sum of squares. If you sum all the yi hat minus y bar squares, you have the explained sum of squares. The residual sum of squares, explained sum of total sum of squares. Now the point is, I need to prove to you that the total sum of squares can actually be broken down into the residual sum of squares and explained sum of squares. I have to prove to you that they both add up. Right? That is, the total sum of squares can be shown as the explained sum of squares plus the residual sum of squares. Intuitively it is clear to you, right? Okay, but we need to prove it still. Right, so if I do E hat I square, right? So if I do summation E hat I square, right, will be equal to so basically first think of squaring this. Okay. So squaring this will be this. Right? Sure? This is clear? Squaring this will be this. Now think of this as A, think of this as B. What is this then? A plus B, the whole square, the A square plus B square plus 2A. This can be written as yi minus y bar square
plus 2y minus y bar
plus y hat I minus y bar square, because I was squaring, so the sign doesn't matter.
plus 2
Minus 2, I think why I am writing minus 2. Why have I written minus 2 instead of plus 2?
if you multiply.
I'll change the sign here.
Okay.
Yeah? Sure? Right? Okay. Now if I sum this up, what do I get? Summation yi minus y bar square. Right? Okay? Plus y hat I minus y bar square. Right? Okay? Now what is y hat minus y bar? Because
Here.
y hat minus y bar is it here? Yeah?
Y.
What is that? So now you have to show me that the total sum of squares is exponent sum of squares plus the residual sum of squares. Do that exercise. Show me that the total sum of squares, if you sum all these and do something to these equations, right? Okay? Actually, let me just rewrite this a little bit more intelligently. Okay? Let me write this as minus. Okay. Yeah? Sure?
Same thing, no?
Same thing, no? If I rewrite this, sure? So what happens? This will become minus and this will become plus. Sure? Right? Now you see some parts. This is nothing but the residual sum of squares. Right? Summation E at I square. What is this? Yi minus y bar, the total sum of squares. Right? Plus yi hat minus y bar, exponent sum of squares, but this part is still left. Right? So this part is plus 2 into summation yi minus y bar, y hat I minus y bar. Right? And then you have to show that this last part will be 0. Right? How will you show that? You have to argue that the last part will be 0. Summation y minus y bar is 0, but it's not summation y minus y bar. No? Summation y minus, each y minus y bar is multiplied by something. So it doesn't become 0 necessarily.
But it is expectation.
Okay, so suppose you think of yi alpha plus beta xi. Right? What is y bar?
Alpha plus beta x.
Alpha plus beta x bar. Take the average on both sides. Average of e bar will be 0. Right? Average of e will be 0. So, what is the first term there? Yi minus y bar will be what? So yi minus y bar is equal to what if you subtract?
Beta xi plus ei plus beta x bar. That is beta.
Yeah?
Yes.
Beta xi minus x bar plus ei. So try to substitute it there and see whether you get some answers.